No.
You're trying to derive a formula, you're trying to come up with a relationship from this. And usually what happens is we make some observations, right? If you were doing this not from a textbook or from history, if you were doing this for the first time, usually the way proof works is you develop some empirical sense before you actually start proving. So maybe you have some examples, things that you can manage. Things maybe like polynomials where you've got y equals x squared, and maybe you have a second function that says, I don't know, let's take f of x is equal to, and we have, x cubed plus x. And you say, hey, what happens if we stick this function into that and we expand it, and we see what the derivatives look like? And you build enough intuition from the result. You say, hey, I wonder if there's a shortcut, and you guess at it. So usually you have some sense of where you want this to end before you start proving it. And the proof of the chain law in one variable usually requires a trick. And the reason I like to share this with you isn't because I expect you to go out and prove things like this, unless you're going to be a career mathematician. The reason we do it is so that you see how we study, or how we manipulate, or how we bend some rules to force things to happen. So this is fascinating. The usual trick is something like, and there's a logic to it. Just for the sake of conversation, do you see what happens if you add k and y? What are you left with? Okay, you're left with just that, right? Cool. So that means I can take this guy and rewrite it like this. Get my order right. Fair? And here's the kicker, right? You look at this, and doesn't that remind you almost of the derivative form? But there is a catch, right? That's the wrong variable. If this is actually like a derivative, you'd want that to be a k. So in order to make that a k, I have to multiply this by something that cancels it. Introduce a k, wouldn't I?
So that represents the chain piece.
So here's my thinking. That's not quite right. That's not going to work, right? I can't just throw something like that in there. But what I can do is, I could multiply this by k over k. I can do that. In theory. So, and if I do that, then maybe I'll just switch these two. Okay. And then there's one last step, which is limit as h goes to 0 of, and here I'm pretty much good to go. And k, that's this, right? So if h if I take the limit as h goes to 0, this guy has a simpler form, right?
G prime.
Yeah, that's exactly right. This guy's a little less obvious, but it's sort of there, right? We said that k is g of x plus h minus g of x, so is, I think we could agree as h goes to 0, this goes to 0. It approaches it.
I do agree.
So as h goes to 0, k is going to 0. This looks an awful lot like the derivative of f of y, right? But y is just g of x, so this is f of g of x derivative. And that's usually, that's the poor man's version of the proof of the chain rule.
It is.
So on the one hand, it's, would you agree with me, it's accessible?
Isn't that proof?
You're not necessarily, we're gonna go out and do it right now from memory, but you can say, okay, I see that. I'm guessing most of us don't come up with this without some serious jail time or some other way of spending a lot of time on it. With nothing to do, but I'm thinking we can see the rationale to it. There's a catch, right? This one is, it's sort of like they let us get away. It was too easy. This one has a catch, and the catch is that someplace in here we're hoping that g of x isn't one of those 0 functions, right? We're hoping that g of x plays nicely so that it's not 0 the whole time, but rather just approaching it. Because if it were 0 the whole time, then that just introduced a serious problem. But those are little things, right? We can work around it. We can just set it as a separate case and say, okay, we're going to assume g of x isn't 0. Anyway, that's what it looks like in Calc 1. Let's take 4 minutes and wander through the version in Calc 3. Okay? And I don't need this to be an all-day affair. In fact, it's important that we have some more practical conversation. Speaking of which, how the chain rule problems treat you?
Number 37.
Yeah, I apologize. That thing's a beast. It's character building though, right?
I just didn't know what you were asking at some point down here.
Yeah. You could probably make a compelling argument that it was much ado about nothing, but it's supposed to be two different ways of arriving at the same result, so it gives you multiple representation, and at least in theory, it's supposed to reinforce the chain rule. But if you go through that thing and you get to the end and you say, wow, that was torture, then you probably don't get what you're supposed to get out of it. So I apologize if that's how that went. However, it is supposed to be educational, so you gotta do it because we're trying to build your experience. And at least your tenacity. Okay? And if you got halfway through it and said, wow, this sucks, I quit, well, then you failed on the tenacity part, but you probably bonus points for intelligence. All right, so a few quick words, and again, I don't want to walk too far down this path. I think I'm officially out of battery. This is the problem. So let me just. This is the conversation that usually comes up here. Chain rule in multivariable calculus has this cool. Bear with me. Cool analogous quality that it looks. Right? It looks similar to the chain rule in one variable. So if we have a single variable for our base function, for where we're ultimately trying to get, then this guy trades in the regular derivative for a gradient, trades in regular multiplication for vector multiplication, or actually in this case, the scalar multiplication with vectors. and then derivative of the inside function. And what we're always hoping for, right, this is essentially implicit differentiation where your implied variable is time. So this is like the proof of implicit differentiation, which is essentially what this is. Okay, so chain rule's biggest selling point is that we use it for implicit differentiation. The implied function is a function of time. So as impressive as it may seem, here's the deal. This is the same concept, right? I'm taking one point and approaching another. I'm taking one value of t and approaching another. This is the definition of my derivative, right? dh dt. So let's just focus on this quotient for a minute. And notice, right? If x, y, and z are all functions of time, then this difference quotient is just this. And like most things, we need a trick. So your trick looks like this. Notice this is a sequence of sums. And what I'm doing, that's why I need battery. All right, so what you're doing is you're telescoping. These two terms are identical, these two terms are identical. The minus and the plus, right? And Calc 2, you saw telescoping series? Same thing, right? So I'm just extending this. And if I write it out again, these are what my parts look like. And then if you go back, to Calc 1 and you visit the mean value theorem, mean value theorem is the one that says if you have a continuous function it's differentiable on the open interval, then if I connect the values, we get the first and last values on the closed interval, mean value theorem guarantees me at least one point in the open interval. Right, where my instantaneous rate of change matches my average rate of change. It essentially says that if your average speed on a highway is 60 miles an hour, that at some point along your drive you're traveling 60 miles an hour. Okay. So we come back and we say, hey, mean value theorem gets used routinely for fundamental theorems, specifically like the fundamental theorem in calculus, where one of the main reasons we have the mean value theorem is to use it there. This is another case where you see it. So here's the deal. You telescope this guy out, you have these terms, and the reason we're doing it is to create open intervals, closed intervals that we can use the mean value theorem on. And here's the way it works. If I look at this guy, right? Look at the numerator. If I take that and write it this way, I know this difference over that. Mean value theorem guarantees me, right? Assuming this is a differentiable function. Mean value theorem guarantees me a point between x and x naught where the partial derivative exists and matches the value of that function there. We're almost done. That's what the mean value theorem gives me. So I go ahead and I replace this expression with this. But it's an algebraic expression, so I can solve this top part by multiplying that over here. And so I get this. So this guy right up here, I'm going to replace with this. We're going to do the same thing with each of these in turn with a y and a z. And what that gets me, and again, I don't want to take too long, But what it gets me in concept is that I can replace each of these differences in the numerators with an expression that looks like this. Now I'm dividing each one by a t minus t naught, so I wind up with this partial derivative and this expression for each one. Don't panic. You're not supposed to reproduce this. You're just supposed to appreciate it.
I already did.
So what I'm doing at the end is I'm looking to create something that looks like what we talked about. So we're almost there. Notice, right, if I take the limit as t goes to t naught,
It's just cheap.
this is a partial derivative. This guy right here, as t approaches t naught, x of t minus x of t naught, t minus t naught, this is a partial derivative. It's just a derivative of x with respect to time, dx dt. dy dt and dz dt. We're trying to bring in the same things. If you were given this as an assignment, right, if I just stuck you with this for a day and said, here, come up with a proof, at least where you might begin would be with the knowing what the result has to be. Knowing that you want the derivative in multiple variables to look like a chain rule. You want it to look like this gradient time, right, derivative of the outer function times derivative of the inner function. And I notice, hey, here at the end, that looks an awful lot like partial derivatives at each point. Now, there is a little catch, right? We've still got C, D, and E, right? These are the mean value theorem values in there. But think about it. As t approaches t naught, I'm shrinking the interval. In fact, I'm shrinking that interval to a single point at t naught, which means really these guys are just going to be partial derivatives evaluated at t naught. And that's usually the conclusion to this. So we draw this generalized statement about taking the derivatives, but what's really implied is at the very end, you're going to evaluate this at x naught, y naught, z naught, or t naught. Anyway, I'm waving my way through it. I'm saying it's a page full of symbolic manipulation. But I don't think there's a line in there that you couldn't at least say, okay, I get that. I don't think there's anything to this that you can't find accessible. And if I put you on stage and said, you present this, you could do it as much service as I can.
Everybody's saying.
Hey, would you look at the time? All right, so that's our proof conversation today. We have one more proof to wander through, not today. It's the one that I alluded to about a week ago when we were talking about gradients and directional derivatives. And that proof is like 3 lines long. So this is just to get you to that point where you say, wow, that one's easy. Anyway, cool? Bear with me. So I apologize about 37. We covered that. But I still want you to have done it. It's a good conversation to go through. At least you find some camaraderie in the misery. And I think there are only a handful of questions to answer. So 37 makes up for the 5 questions I didn't ask you. 20, on the other hand, excellent example. If that worked out, got yourself on the back. And 23.
It's a pure graph.
Which is all about graphing. That's exactly right. Does it go okay? You'll get back to me on that? It does not go okay because you tried and really were lost. It does not go okay because you haven't tried it yet. Don't answer that. I'm just saying. So 2023, you want to have done. Let me say that. 2037, there's no way that shows up on a test. I hope you'd know that. It's pretty obvious, it's long, it's involved. But the tenacity, the perseverance that it requires to get through that you do want on a test, because then they give you problems where you have to take derivatives and you have to slog through it, and you have to know that you can see it through to the end.
Yeah.
So, tell you what, until I hear otherwise from you, let's go a little further down the road. Maybe we could do that. So, if you've noticed, a lot of the conversation we have in Calc 3, sooner or later, builds on what you've done in Calc 1. And if you read ahead, if you already did the Wiley class reading, then you know where this ends. Tell me about the second derivative of this function.
I forgot there's something called second
What do you know about the second derivative for that function?
constant.
We agree about that?
I think it's
Is that a yes?
second derivative.
Awesome. I'm going to go ahead and one, assume you know why, and two, assume you don't know why. So here's my logic on this. I noticed that in this case, the slopes, right? If I look at this function, I look at all the tangent lines. Those tangent lines have slopes that are decreasing, right? They started out big positive and became less positive, 0, and then became more and more negative. So as x increased, my dy dx decreased.
Yeah, it's making it something.
The rate of change in my derivative function
It's constant.
is negative. My derivative function is a decreasing function, right? Because it's decreasing, its derivative is going to be negative.
Because the second one
Okay?
is
So this is the rate of change and the rate of change.
I know.
And that's why you get concave down.
Yeah, that's in here.
I'm just going to leave that hanging in the air for a minute. Okay? So here's the deal. I just happen to have with me this guy. And what's a good function for this?
Something that I don't know.
Stop.
You treat it badly, it will treat you badly.
What would be a good function for that? 0, 2, 4, let's call that 5. Could you lean over, tell anybody near you a formula for that, and then tell me? Oh. Whose little literature book is this? Anyone?
Little
Anyone?
bit.
Okay, well,
Literally.
the next stop is Craigslist. I want you to know there's good money out for this guy. It has Emily Dickinson in the front of his piece. Come on, let that go.
You'll get like $2 out of
I don't
them.
know if you have to say, because then you'd have to, maybe, you know what I mean? It's not
Worth
really.
of potatoes.
You don't think so?
It's not perfectly rounded.
It looks perfectly round. Yeah.
Yeah, don't make this more interesting
don't.
than it needs to be.
It's just gonna be negative x squared minus y squared plus y. Or no, minus y. Because it's
Minus
negative x squared.
Negative parentheses x squared.
Yeah, you could say it that way, it's easier.
Give me something. I'll start. What else you got? Excellent.
Yeah, you do that.
I'm going with it. Cool. Keep that in mind. Good. Here's what I'm wondering. If you were to look, if you were looking at this parallel to the xz plane, right? So I'll pick a point on this so that I can kind of cheat.
Because no, it's too.
So here, suppose I pick this point. Right. If I look at that point and I look parallel to the xz plane, so that wall, right? So I'm really looking, like we do in Calc 1, at a function whose cross-section looks like this, right? So in the xz plane, I get this inverted parabola, right? In fact, in the xz plane, y is 0, and I'm looking at that parabola. Cool? So here's my question to you. If I look at slices parallel to it, say like the one that goes through this, can you see the curve that this point is on, parallel to the xz plane? It's a yes, no question. I get a few nods. You see that slice? So my question to you is, relative to the xz plane, so just in terms of z, in terms of x, what would you say is true about the concavity of the curve that goes through this point? That is, this curve. Alrighty then. Can we agree about that?
I can.
Not unlike that guy, right? Still okay? So I'm looking at it in terms of xz, right? Parallel to the xz plane. I'm looking at something that looks like this. And I'm looking at this parabola, parabolic slice. And here's my point, and I'm saying at that point, and in fact, could we agree that at every point on that curve, this guy is going to be concave down? Cool. Then the issue is, how do I describe that thing? Okay? How do I describe that? How do I describe that behavior? Well, here's what I'm thinking, is if I looked at the derivative of z with respect to x, that would tell me, at that point, it would tell me the slope of a plane perpendicular to the xz plane. It would tell me how this guy was sloped coming out the x-axis towards you. So if I were writing the equation of a plane, I took dz dx, that would give me one of the two slopes that I used to describe the tilt of the plane. If I took the second derivative of z with respect to x, I think that tells me the concavity in the direction of this curve. So I'm going to make the suggestion, I'm going to offer up to you that right here at this point, I think, and we'll come up with a name for that later, for now we'll just call him A. So I'm going to say at A, I think the derivative with respect to x 2 times, I think this guy is going to be negative. Okay. I'll take that as a wait and see approach. That's fine. You can wait and see. Well, this has an obvious next thought. I'll let you think it. While you're thinking it, I'm just going to go over here and draw in this curve. You know what's coming. So I'll draw it in that curve. We'll put it over here.
I think someone can probably move on to move to go to the city and change it.
Same thing, right? And this time I'm looking at something that looks like this. You tell me. What do you think's true about that curve?
Concave up to x.
Concave down to mean, right? Still down.
What for
Fair.
x?
So I'd say in both directions, my second derivatives would be 0. And you see why I would call that
If you look at it
second
that way,
derivative with respect to y?
I don't think that's really important.
Do you see how it has nothing to do with the rate of change in x? Okay. Okay, cool, excellent. Excellent. You know that's the easy part, right? So what am I leaving out?
X, Y.
So true. So that's the usual part of this conversation. We're looking for a way to understand what these things are. And to me, if I look at these in terms of slices, right, in terms of derivatives where I can get rid of one of the variables, then I can think in terms of, okay, second derivative with respect to x. I get that. That's leaving y out of the conversation. So it's anywhere parallel to the xz plane. Whereas if I do the other direction, I could also look at any plane parallel to the yz plane. That's coming out towards you. And if I look at just those two directions, we're in pretty good shape. Where it starts to become a little more fascinating is, yeah, when I mix my partial derivatives. So this is usually, right, you can imagine this is one of the things that makes multivariable calculus more interesting. Because you don't get this option in Calc 1. You're going one way. So let me erase this guy for the time being. And let's suppose that we started with fx. Cool? If I start with fx, fx is describing the slopes, right? Just like this guy. It's describing the slopes at each point. And if you follow the x-axis going out of here, you see what's happening, right? Those slopes are coming up, 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 and they're coming down, 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 down. So as x increases, it's just like we talked about there, as x increases, these derivatives are becoming, on the backside, they're positive, but getting smaller. Here they're 0, and as I move forward, they're becoming more and more negative. And that's why we have a second derivative in the x direction that's 0. Sorry, it's less than 0. So my question then is, well, let's look at this point and consider, right, so forget all this other stuff for a minute. Let's consider the tangent line at that point. It looks like this, right? Kind of picture the edge of a snowboard. Ski if you prefer. We okay? So that's what happens as I look at fx. Now here's the question. If you're on the snowboard and you're riding it, right? So you're catching this edge. You're on the downhill side. And that's looking pretty steep. But you're on that downhill side holding your snowboard. Well, you could ride straight down the mountain this way, couldn't you? But you could also keep that edge, and instead of following the line here, you could ride that edge down this face instead.
I don't think that's possible.
You clearly have not been in the snow enough, my friend.
A long time ago.
Exactly. I will tell you, I bet I got a half dozen snowboarders right here, and a few people who aren't here are probably off snowboarding, who could nail that. So here's my question to you. If I look at this guy, as not as following the trajectory in the x direction, but if I looked at this guy as it slid down holding this edge, sliding down this face in the positive y direction, what's going to happen to the angle, the tilt of that edge? It's a good question, isn't it? And I'll tell you what, as I look at it, I don't know about you, and it's hard on 3D surface, but it's a little, I look at it and I'm thinking, here's my original point. If I went to the next one, I'm thinking, that's not showing me a whole lot of difference. So hard to tell, hard to tell. We'll look at one in a minute where it's a little better. You notice I'm going down this hill, these guys aren't flattening out a whole lot. And in fact, let me erase this for a second, now that you have that after image in your head. Look at these contour lines. look at their slopes. What do they look like? If I look at these contour lines as I move in the y direction, what do you notice about this slope and this slope and this slope? What do those look like? They look parallel to me. They look to me like that fx that you have, the slope in the x direction, it looks to me like it's not changing.
That's all.
Okay, so that's the mental image you want to have. We'll come back and do one in a second. It has a little more fuerte to it. But in the meantime, consider this. We do have a formula that probably fits that guy. Let's do what we did in calculus. One, to assess what's happening. So here's your mission. What is fxx? What is fyy? And I don't think we need to worry about which point, because you can see I could have picked almost any, well, I could have picked any point except the one at the very top, and we would have gotten, well, even at the very top, yeah, it doesn't matter. Could have picked any point, and we still would have gotten the same result. So let's see what happens. Would you find those guys? And then let's talk about fxy. Okay? Time's up. Yeah. Hey, what's fxx? What's fx? Okay. So we can agree that fx is equal to negative dos x. How about? Never mind. How about fy?
Negative 2y?
Yeah, it's just not as entertaining. All right, cool. So what is fxx?
Negative 2?
Exactly. Which is what we have in Calc 1, isn't it? Take two derivatives of a quadratic, you get a constant.
Fucking compliment.
How about this guy? Lo mismo. All right, if I have the derivative of x, what happens if I take the derivative with respect to y now?
Zero.
Yeah, I get 0. Which means when you have a derivative that's 0, what does that tell you?
No kernel.
Okay, later. It tells me, yeah, what I'm hoping that tells me is that I have no rate of change in my rate of change.
It's like
It
Harrison.
means my rate of change stays constant. So what it suggests to me is what you see here, which is that those look like they're staying the same all the way down the hill. Just out of curiosity, if I have the derivative with respect to y and then I take the derivative with respect to x, you get 0. Okay, so good. Los menos, not too bad. Let's look at one more, if you don't mind, that's maybe not quite so obvious, as you might imagine. So, cool. So we can scare this guy up. He's here someplace. I think it's this one. Yeah. Always a good time.
9/11. For sure.
Like an E saddle, right?
Really?
Like that?
Yeah. It's like a saddle with E.
God, it doesn't. Okay, it's not an online dating service for
Right,
cowboys.
exactly. You
got a saddle.
Yeah.
Awesome. All right, very nice.
That thing
so
will crush your balls for
this
sure,
is
bro.
one where I actually don't want to share the formula with you. Partly because I don't want you to use a formula. Let's pick a point. Let's go with, say, this guy. And here's my question. This is so we'll take it right out about here.
Guess it can be straight.
Okay, so that's my x-axis, and this guy is my y-axis.
Parallel.
I did not draw that very well. Sorry. And that's how it should look. There's my x-axis. Okay, and getting better.
Yeah, a bit.
I'll
Yeah,
take
if
it.
you.
It's fine. Okay. Anyway,
That's
you get the
not-
plan.
no.
So here's my question to you.
No.
Could you give me the sign of F? No, let's go Fyx.
Shit.
Could you give me the sign of Fyx at this point? Would you talk that over?
I think it's legal.
So the
I mean, it's
question
legal.
is, you picture a snowboard tilted in the right parallel to the YZ plane. You picture its tilt in the YZ plane. The question is, as you move that forward in the X direction, how's the tilt going to change?
He must be
Okay,
fun.
so-
He must be
Yeah,
fun
that's not-
snowboarding with bro.
Spitting out equations.
Let me put you on the side and see what happens with your derivative, bro.
But it's becoming less common.
Bro, you sure I'm not gonna?
Okay, so
There's some people.
think about, like you said, you're on the surface, right? In the Y, you're on this surface, right? And you're coming
I
like
kind of
that.
just switch my brain with that.
Kind of what's happening
Yeah.
to your,
Is it retarded?
yeah. So it should be fine.
Oh, at that
Barely,
point,
but-
that's going up.
Isn't it? Yeah. Isn't it positive?
No. It's not going up. It is coming this way. What I'm saying is the curl is not getting more negative. Actually, I don't know, because if you go directly in, so you're going like this, look. So you're coming down and you're kind of like flat. So spacey one.
Okay, I appreciate that you at least humored me for a brief conversation. That's lovely. This is Fy. Tell me about Fy. What do you notice?
Kind of keep down. Negative.
Just tell me about Fy.
Yeah.
Negative.
Do we agree about that?
Negative.
Yeah. So again, you're on your snowboard. It's tilting downhill, right? This positive y-axis. So if I look at z and y, this guy is definitely negative. Fair?
Which way is
Because that way is positive y, that's positive z. This guy, right, in the yz plane, that guy's looking like this.
it? Just one.
So I'm just asking about Fy. Cool? So my next part of this is we're interested in Fyx, which is essentially around this point, what's happening. So we're going to take an extreme approach and look down the road. If I were to slide downhill in the x direction, what's going to happen to this snowboard's edge? What's going to happen as I go down the hill?
Get smaller.
It's going to look like that, and then it's going to look like that, and then eventually it's looking like this, right? So as I plot down the hill, what's my snowboard's edge doing? Okay, but can we agree it went from a negative slope like this
To a less.
to less negative? So can we agree that technically Fy is increasing in the x direction? That is, as x gets bigger, Fy is becoming less negative.
See, it's like,
So as x increases,
You going like this?
yeah. It's the curl.
Fy is becoming less negative. So, can we agree that Fy in the x direction is increasing? Okay. Is that what you were thinking?
Exactly what I was.
Okay, this is the one that shows up on the second exam that everybody looks at and says, I don't know what you're talking about. So if that made sense, awesome. And if it didn't make sense, come back and visit me with, hey, that didn't really make sense. So could we talk about it further?